Okay, so welcome to Math 150. This is Lec23. So what we're going to do today is Lagrange multipliers. Like a lot of multivariable calculus, the amount of calculus in this lecture is extremely small. We essentially jump in, do a very quick set of partial derivatives, and then we jump back to doing a lot of algebra. When you are doing a homework problem, when you're doing an exam problem, you have a tremendous advantage over problems in the real world. What should be true about a homework problem or an exam problem about the algebra? What kind of answer? Usually the answer will be, so it'll often be a whole number, it'll often be some kind of nice answer. It's not going to be disastrous, horrible, horrendous algebra. So you know that you should be able to find a good way through all the calculations that are happening. That is not necessarily going to be the case in real world problems. A lot of this is because we deliberately choose problems that have simple algebra to really emphasize the point. And so the goal is we want to talk about how do we find maxima and minima, or at least candidates for maxima and minima for functions of several variables. For functions of one variable, it wasn't so bad. We look for where the derivative is 0, and those are the critical points, and then we check the endpoints. In one dimension, the endpoints is not that bad. There's only 2 candidates at most, maybe less if you're looking at the entire real line. But all of a sudden, if we're in several variables, there are so many possibilities for the endpoints if we're looking at a constrained maximum and minimum. Say I want to be on the surface of a sphere or inside, and I want to see where is my function largest. Now I have infinitely many points on the boundary. So the question is, how do we find the candidates? Well, it turns out we can break this up into 2 steps. So there are 2 steps for optimization of several variables. So optimization in several variables. We have the interior points. So we look for the gradient of f is equal to 0. Is that 0 the number or 0 the vector? So which is it? We want the gradient of f to be 0. 0 the number or 0 the vector? 0 the vector, because the gradient is the vector of partial derivatives. So this would be df dx1 ... df dxn. And this is really straightforward. This is essentially just what you've done in Calc 1. If I'm at an interior point, well, just fix all your directions but one, fix all your variables but one, and only move in one direction. Now I have a function of one variable, and so from one variable calculus, the derivative in that direction has to be 0. So the gradient must be 0 at an interior. And then the more difficult one is the boundary. Say we have the surface g of x1 ... xn equals some constant c. Then must have a lambda such that the gradient of f is equal to lambda times the gradient of g at a candidate. So again, these are only to find candidate points. These are not guaranteed to be places where we're going to have a maximum or minimum. The idea is, the hope is that there won't be that many things to check. And if there aren't that many things to check, then we should be in good shape. So the first thing to look at in something like this is, well, how many equations do we have? If I have n variables, x1 through xn, and I've added lambda, let's write down all the equations. So we have df dx1 equals lambda dg dx1 ... df dxn equals lambda partial g partial xn. And then we also have g of x1 through xn equals c. So we do have n plus 1 equations. We have n plus 1 variables. It's at least possible. If we had more equations than unknowns, what do you think would happen if we typically have more equations than unknowns? What do you think about the number of solutions? So imagine we have more equations. Maybe what's the simplest number of variables to have? 1. So give me 2 equations involving x. So x equals 1. And what's your second equation? X equals 0. So if I have 1 variable but 2 equations, unless the equations happen to be the same, I'm not going to get any solutions. So if I have x equals 1 and x equals 0, there's no solution. If I have more equations than unknowns, it's almost surely the case that there's nothing that works. Of course, I could jiggle things and I could give you the same equation multiple times. I could give you x equals 1 and I could give you 2x equals 2. Well, if x equals 1 and 2x equals 2, it's not that hard to solve for x. X equals 1, the 2 equations are really the same. So in a situation like that, we're fine. Typically, generically, if I give you more equations than unknowns, we expect them to be inconsistent. What about the other direction? What if I give you fewer equations than unknowns or more unknowns than equations? What do you expect to happen in that case? So the simplest case before was we had 2 equations in 1 variable. Now I want 1 equation and 2 variables. So somebody give me an equation involving 2 variables. X plus y equals 1. So I would have infinitely many solutions now. You give me any x, I can find a y. So if I have more variables than equations, I expect there to be infinitely many. In this perfectly balanced situation, I expect there to be finitely many solutions generically. I don't expect that there's necessarily just one solution. If I give you x squared equals 1, how many solutions are there? 2, right? There's 2 solutions, even though it's 1 variable, 1 equation. But it's finitely many solutions. And so we go from basically expecting no solutions, infinitely many solutions, finitely many solutions. So this is perfectly balanced. Notice that the amount of calculus we need to do is extremely minimal. We just take the partial derivatives and set them all equal to each other. From this point onward, it is just algebra. It's n plus 1 equations with n plus 1 variables, do the algebra, and find all the candidate points. Once you find the candidate points, that's when you can do things such as the second derivative test or various other things to tell if it's a maximum or minimum, or sometimes you can just tell from physical grounds whether or not it's going to be a maximum or minimum. You might be trying to figure out what's the largest area you can have for a given perimeter. If I give you a fixed perimeter, can you make the area arbitrarily large or can you make the area arbitrarily small? Which can you do? So if I give you 100 meters of fence, can you make the area arbitrarily large, that it's enclosed, or arbitrarily small? Small. You just make it really, really, really thin. Can you make the area arbitrarily big? No. So if I'm trying to find candidates for the maximum and minimum, I know I can make the area go all the way down to 0. I know I can't have it go up to infinity. If I find a candidate that's not giving me an area of 0, that's got to be the maximum. So I know from physical grounds, I'm not finding another minimum. Okay, so the question is, why does this work? The interior, again, we've already seen from Calc 1 why the interior condition holds. I'm just looking for places where the gradient of f is 0. That just means all the partials are 0. But for the boundary, why am I looking for some number lambda such that the gradient of f is equal to lambda gradient of g? Well, remember, vectors have 2 parts. They have a length and they have a direction. If I multiply a vector by a number, do I change its length? So if I multiply a vector by 2, what do I do to its length? Is it unchanged or have I changed the length? I changed the length. How much have I changed the length by? By a factor of 2. Have I changed its direction? No. And then we can argue, if I multiply it by -2, have I changed its direction? You can argue, right? I can be convinced either way as to have you changed its direction or not. It's still pointing along the same line, but it's now flipped 180 degrees. So if I look at gradient of f is equal to lambda gradient of g, that's saying the gradient of f and the gradient of g are in the same direction. So let's try to talk about what this can do. So imagine we have g of x1 through xn equals c. This is the level set of g of height c. So I'm looking at all points that are at height c under g. So for example, maybe I have g of xy is x squared plus 4y squared equals 3. Anybody know what kind of object this is? That's an ellipse. And so if instead of doing 3, I did 1, what kind of object would it be? Still an ellipse. So for different values of c greater than 0, it's an ellipse. And so maybe here is c equals 1. Maybe here, c equals maybe 2. And so I can look at all the points x and y such that x squared plus 4y squared is some fixed value c. And now imagine I have some curve on my level surface. Well, on an ellipse, I really have no choice. I've got to just walk along the ellipse. I could, of course, give you something a little bit more interesting. I could give you an ellipsoid. X, Y, Z is, say, x squared plus 4y squared plus 9z squared equals c. So cultural extra credit, what movie has a monolith that's 1 by 4 by 9? All right, so x squared plus 4y squared plus 9z squared is an ellipsoid. I now have lots of different ways I can walk on the ellipsoid. I can walk on the ellipsoid maybe in this direction. I can walk along the ellipsoid maybe in this direction. I could go on some kind of diagonal path. You give me a different curve, and I have some path that goes. So let's imagine some curve R of t on the ellipsoid. And so let's look at the function a of t is g of r of t. What is that function going to be if I stay on the ellipsoid of value c? What will g of r of t equal? So if I'm staying on the ellipsoid, x squared plus 4y squared plus 9z squared equals c, and I always stay on the ellipsoid, what will g of r of t equal? Yes, it's just c. I'm just staying on the ellipsoid, right? I'm telling you, I'm staying at a height c. I'm choosing some r of t that's always on the ellipsoid of height c. So there's two different ways we can take the derivative of this function a of t equals g of r of t. Can somebody give me one way we can take the derivative of this function? How could we take the derivative of this function? Yes, we could do the chain rule. And this would give us, by the chain rule, we would get your a prime of t is the gradient of g at the point r of t, dotted with r prime of t. So that's one way to take the derivative. What's another way to take the derivative of the function g of r of t equals c? Yeah, the derivative of c. I'm telling you, this is a function of t. For every value of t, I'm going to give you back the value c. I must be in a very generous mood today to give you such a nice function. What's the derivative of a constant function? 0. So by looking at this two different ways. By looking at it as a function of t, its derivative is 0. By looking at it as a function of, it's a function of x, y, and z, and x, y, and z are functions of t, and we're on some path that's staying on the surface, I have the chain rule. What this is telling us is that at every t, the gradient of g at r of t is perpendicular to r prime of t, which is the tangent to the curve r of t at t. So the gradient of g is the normal direction. So we talked a little bit about one way to view a plane is all vectors going through a base point that are perpendicular to a given direction, the normal to the plane. The gradient of g, if I'm looking at all the points x, y, and z on the level set C, is going to just be the normal to the surface. So at any point here, the direction is going to just be the gradient of g. So if we think about what's going on, if I give you some surface, I want to find the maximum, I want to find the minimum of my function on a surface. The gradient of g tells me the direction of the normal to the surface at that point. If I have some curve r of t in the surface, r prime of t is telling me what direction my tangent is at that moment as I travel along the surface. And if I'm traveling along the surface, then at every moment I have to be perpendicular to the normal. So what's going on is the following. Imagine, here's my surface. And at some moment in time, here's r prime of t. So that's the direction it's going. And here is the direction of the gradient of g. Imagine the gradient of f is in some direction. Well, what I can do is I can write the gradient of f as something in the direction of r of t and something in the direction of the gradient of g. If I'm staying along the surface, if I'm staying in the surface, I want to know, how is my function changing as I move just a little bit? That's a directional derivative. So how I change, so if move on surface, the change is a directional derivative. So it would be the derivative in the direction of r prime of t of f. And so that would be the gradient of f at r of t dotted with r prime of t. So if I'm traveling on the surface and I want to know, how much does my function change if I move just a little bit? Well, I'm just calculating the directional derivative. So notice that if my function has the gradient of f that is entirely in the direction of the gradient of g, then there's nothing that's in any direction I can move. Oh, and that means all the directional derivatives will be 0. And that's a candidate. So if the gradient of f is only in the direction of the gradient of g, then all directional derivatives of f as stay on the surface are 0. So we have candidates for max and min. If the grad f has something perpendicular to the gradient of g, move in that direction for the maximum increase and opposite direction for maximum decrease. So this is why the conditions I told you work. If the gradient of f is aligned with the gradient of g, then no matter what direction I move, all my directional derivatives will be 0. So that means my function is not increasing locally if I move in any of the directions. We have to be a little bit careful because remember, there are still functions such as x cubed, where its derivative is 0 and it's not a maximum or minimum. So a better way of looking at this is if the function gradient of f has a component that's not perpendicular to the gradient of g, then clearly if we move in that direction, things are increasing. And if we move in the opposite direction, things are decreasing as much as possible. So the only chance we have for maximum or minimum is when the gradient of f is in the same direction as the gradient of g. If the gradient of f has any component perpendicular to the gradient of g, just move in that direction to see increase, move in the opposite direction to see decrease. That's where these conditions come from. Okay, any questions about this? So this is used a lot in economics to try to optimize various things. This uses a lot of the concepts we've had so far in the semester. You know, why do we care about level sets? Why do we care about directional derivatives? Yes. You just have to calculate it. You know, I'm giving you some function f that we're trying to optimize. And so if I want to try to optimize it, if I'm inside the surface, I just look for where is the gradient of f equal to 0. Because if I'm inside, well, if the gradient of f is not 0, well, then just move in that direction, you increase, move opposite that, and you decrease. When I'm on the boundary, I can't just say, well, just keep moving. So over here, if I wanted to get things larger, well, just move in that direction. Well, I can't. I have to stay on the surface. So because I have to stay on the surface, it doesn't matter that I want to move in that direction. I'm not allowed to. But the way I've drawn things here, this choice of gradient of f does have something in a tangent direction to the surface. It does have a component where if I move in that direction, if I move in that r prime of t, my function will get a little bit larger. So I can't be a maximum here. Conversely, if I move in the opposite direction of r prime of t, I'll be getting smaller. So I can't have a minimum here. So this, if I want to have a candidate for maximum or minimum on the surface, the only thing that's left is if the gradient of f is parallel to the gradient of g. So think of it as if I'm stuck on the surface, you know, I want to go in a direction where the directional derivative is positive. If I go in a direction where the directional derivative is positive, then my function is increasing. Well, how do you calculate the directional derivative? It's the gradient of f dotted with r prime of t. But we know, remember, recall the gradient of g at r of t dotted with r prime of t is equal to 0. We know the normal to the surface is perpendicular to every tangent direction. So we want to try to find a way to determine, is this point a maximum candidate? Is this point a minimum candidate? We know every time we take the gradient of g at a point, it is always perpendicular to any direction we can move staying on the surface. If the gradient of f is only in the direction of the gradient of g, then we know all of these directional derivatives have to be 0. Imagine, however, that the gradient of f is not in the direction of g. If the gradient of f is not in the direction of g, then it's not just a multiple of the gradient of g. It's got to have something perpendicular to that. Choose r prime in that direction, and now all of a sudden, my directional derivative is positive. Choose r prime negative of that, and all of a sudden, my directional derivative is negative. So the only candidates I have for maximum and minimum are where the gradient of f is parallel to the gradient of g. Does that answer the question? So now that explains where all these conditions come from. You know, I want to solve the gradient of f is equal to some multiple of the gradient of g. They're going to be in the same direction. So I just have to take the partial derivatives and solve the system of equations. And you've got to be very careful when you solve the system of equations. So let's start off with, for example, let's say f of xy is 4x squared plus 2y squared. And let's say g of xy is, let's say x squared. Let's do x to the fourth and 2y to the fourth. X squared plus 4y squared equals 1. Yes?
You said that you only have
we are, for the interior, the candidates are where the gradient is 0. For the boundary, the candidates are where the gradient of f is parallel to the gradient of g. So if we want to have candidates, so the first thing to do the interior. So for the interior, we need the gradient of f to be 0. So the gradient of f is df dx, df dy. So can someone tell me what is the gradient of f? (16x cubed, 8y cubed). So if it's 0, 0, we need xy to be 0, 0. So this is clearly going to be a minimum. How do I know this is a minimum? Well, I mean, I could do a second derivative test, but this function is actually going to be a nasty function for the second derivative test. All the second derivatives are going to vanish. But if you look at it, x to the fourth and y to the fourth, these are always non-negative because they're fourth powers. And in fact, they're always positive unless it's 0. So when I put in 0, 0, that's the only time f of xy is going to be 0. Any other choice of xy is going to give me something positive. So I know 0, 0 has to be a minimum. Okay? Now I need to try to find the maximum. Does anybody have any guesses where the maximum is going to be? Well, we're now on g of xy is x squared plus 4y squared. We have to try to figure out what values of x and y is going to give us a maximum. So when you look at this, when x equals 0, what does y equal? 1/2. And when y equals 0, x equals 1. So it's going to look something like this. So this will be x squared plus 4y squared equals 1. So if you look at this, I claim there's a natural candidate. Anybody have any thoughts as to what might be a good candidate? So we're trying to maximize the function 4x to the fourth plus 2y to the fourth. Do you want to make x large? Do you want to make y large? Do you want to make both large? You'd love to make both large. Can you make both large? No, what happens the larger you make x? What happens? The smaller y becomes. Well, which do you think is better for you? You have 4x to the fourth plus 2y to the fourth. Which helps you more, larger x or larger y? I'm sorry? Larger x. And so it looks like I would much rather have a larger x than a larger y. I've got the 4x to the fourth over here, and I can get x much larger than y. If I had to guess, I would guess 1, 0 or -1, 0 would be the best choices. So let's go through and calculate things. So for the boundary, we want the gradient of f to be lambda gradient of g, and g of xy equals 1. So we're going to get the gradient of f is, we already know that. The gradient of g is going to be 2x, 8y. because that's the boundary constraint. That's the surface we're on. Right, we're trying to maximize this function. So, find max min of f on and inside g of xy less than or equal to 1. So I didn't write that down explicitly. G of xy equals 1 is the boundary, and then less than 1 is the interior. So frequently in these problems, you write down what the boundary is. That's where you have to do the real work. The interior is not so bad. So we get 3 equations. The first one we get is df, we get f sub x is lambda g sub x. We get f sub y is lambda g sub y, and we get g of xy equals 1. So f of x is 16x cubed is equal to lambda 2x. Then we get 8y cubed is lambda 8y. And we have x squared plus 4y squared equals 1. So when you look at this, we have to somehow solve. We have 3 equations, 3 unknowns. How would you solve 3 equations with 3 unknowns? Substitute. So can you see any nice way to eliminate some of the variables? Yes.
G equals 2x 8y.
Well, g of xy is x squared plus 4y squared. So when I take the derivative with respect to x, I get 2x. And then the other one would be 8y. Yep. So I have 3 equations and 3 unknowns. I could take the second one and find x is equal to 1 minus 4y squared, take the square root of that, and get your x is plus or minus the square root. Yeah, what else could we do? I'm sorry? What y squared is equal to what?
Divide by 8y on both sides.
Okay, so you can try to solve for lambda. There's a problem. Are you a physicist or an economist? Or are you a mathematician today because you're in a math class? But today you're in a math department. So what do you have to be careful about if you're in a math class before you divide? Making sure that it's not 0. So we have to break it up into cases. So case 1, so let's break it up into cases. So case 1, if x equals 0, well, if x equals 0, then it's very simple, right? In that case, we then get 4y squared equals 1. So y equals plus or minus 1/2. Case 2 is y equals 0. And then in this case, we get x squared equals 1. So x equals plus or minus 1. And then case 3, x and y are both not 0. And now that we know x and y are not 0, now we can divide by the 8y if you want. And so you just have to be very careful to break it up into cases. What I would actually do is I would actually take the ratio of the first divided by the second equation. So divide first by second equation. And this will give you 16x cubed over 8y cubed equals lambda 2x over lambda 8y, or 2x over y cubed is equal to 1/4 x over y. And so that's really nice. We know x over y is not 0. As x divided by y is not 0, we get x over y squared is going to be 1/2, or x squared is 1/2 y squared? Yes? So now we have to solve. How do we figure out what the solution is now? We know x squared equals 1/2 y squared. Do we have any other equations we can use? Yeah, now use x squared plus 4y squared equals 1. So we get, so the question is, do you want to say x squared equals 1/2 y squared, or do you want to say y squared equals 2x squared? Okay, so then we would get 1/2 y squared plus 4y squared equals 1, or 9/2 y squared equals 1.
Wouldn't it be 1/2 y squared squared?
No.
It's x squared. Oh, x squared.
It's x over y quantity squared. It's almost like I chose these numbers at home to make things work, or have done this for so many years that I don't even need to choose them at home. So now we get y squared equals 2/9. So y equals plus or minus the square root of 2 over 3. And then what will x be? If y is plus or minus 2√3, what would x be? So x is going to be plus or minus √2 over 2 times y. Right, because if x squared is 1/2 y squared, then x is going to be plus or minus √2 over 2y. So when I plug that in, I will get x is equal to √2 over 2 times y. So I'm going to get, I think, 2/6 plus or minus 2/6. And so here are my candidates. They're the points plus or minus 1, 0, 0 plus or minus 1/2, and then plus or minus 2/6 plus or minus √2 over 3. So how many points are there? Not 3. I get less. I get 8. I get 8 points. So check. So I will let you check all of them. Okay. And then you just go through and check and see which of the 8 is going to be largest, which of the 8 is going to be smallest. 8 is not pleasant. It's not horrible, especially since plus or minus 1, plus or minus 1/2, and the pluses and minuses, they don't really matter. There's only really 3 distinct types of points, because when I'm putting them into my function, I'm raising things to the 4th power, so the signs don't matter. So there's check all, but really only 3. What it's just saying is there's a lot of symmetry here. And that's all you have to do for problems like this. The hardest part is that you might accidentally forget something when you divide. So you might end up at a saddle point. So this could be a saddle point, and maybe one of these is the maximum. So before you do any division, always ask, am I dividing by 0? Now, at the end of the day, we're trying to find where is the function largest or smallest. Certain types of discrimination are acceptable in mathematics. Okay, I'm going to be very careful because this is being recorded. What are we looking for at the end of the day? I'm trying to find where this function is largest and smallest. What am I looking for? The values of x and y. I couldn't have phrased it better. Do I give a shit about lambda? You don't know that. You have no right to say, I don't give a shit about lambda. I may not, I may. I'm being silent on my views on lambda. But if I just care about finding where's this function largest to smallest, do I care at the end of the day about what value lambda takes on? No, lambda is just a helping variable. I need n+1 variables with n+1 equations. Lambda is my extra variable. But at the end of the day, I don't actually need to solve for lambda. For these points, when x is plus or minus √2/2y, could I find out what lambda is? Of course. I could plug it in and I could solve for lambda. But there's no need. At the end of the day, I just care. Now, lambda might actually have some physical meaning, talking about how many copies of f, of the gradient of f, do you have in the direction of gradient of g. But when I'm trying to solve the problem, I don't actually care about the value of lambda. Because I don't care about the value of lambda, okay, so now I'm being very clear. I don't care about lambda. Because I don't care about lambda, the very first thing I did is I divided equation 1 by 2 because that got rid of lambda. And because it got rid of lambda, that was fine. Yes. Yes.
2 is x y cubed equals 1/4 x y.
Oh crap, did I do it the wrong way? It should be 1/8.
Yeah,
I wish you'd said that earlier. Yep, that should be 1/8. So this needs to be fixed. And that should be a 1/8 over here. So that's going to change things a little bit. So that should be 1/8. So then we have x squared equals 1/8 y squared. So x is going to be, when I take the square root, it's going to be 2√2 down below. So it's going to be √2/4, I believe, right? Yes. And so now x squared is 1/8 y squared. So this changes it a little bit. So it's 1/8 y squared plus 4y squared. So now it's going to be 8 times 4 is 32 plus 1 is 33 eighths. Is that right? Okay, so then we get, so y squared is going to be 33 eighths. So y is going to be plus or minus, fix those. Okay, so it's going to be plus or minus, I'm just going to leave it a square root of 33/8 in the interest of time, and x is going to multiply that by √2/4, so it's going to be plus or minus the square root of, I think, 66 over 8 times 4 is 32. Oh, wait, the 8 is inside the square root, right? All right, so 66 over 4 square roots of 8, yes? And so then we'll just feed this in here, and then we'll get square root of 66. And you can easily simplify this a lot. And y is going to be the square root of 33 eighths. So you can just check those. Okay. Now there's one thing I want to remark for this problem. So I gave you g of xy was x squared plus 4y squared equals 1 is the boundary. And I gave you f of xy is 4x to the 4th plus 2y to the 4th. There is a way to reduce to one dimension. And the way to reduce to one dimension is I could let x equal 2 cosine theta, y equal sine of theta, x squared plus 4y squared is going to be 4 cosine squared theta plus 4 sine squared theta equals 1. This is a parametrization of my boundary curve. And so now f of x of theta, y of theta is going to be 4 x to the fourth, so it's 2 cosine theta to the fourth plus 2 sine theta to the fourth. This is just some new function. I'll call that maybe script f of theta. And find f prime of theta equals 0. Actually reduce this to a function of one variable. Now, is everybody clear on this? Yes.
This isn't just converted to polar, right? It's not
well, an ellipse is a circle if you discriminate a little bit about the directions. And so what I'm basically saying here is I have to weight the x-axis more than I weight the y-axis.
Oh, wait, and you're just plugging in 2 and 1 for r.
Right. So it's not quite polar coordinates. In polar coordinates, I have to use the same radius for both. So well, my function f of x, y is 4x to the fourth. Yeah, I'm just using the same I'm using the same function from before. And so now I can actually do this for all values of theta. I don't have to just do theta from 0 to 2 pi. There are no endpoints. I just look at this function and just see where is this function. This is just a Calc 1 problem. Now, unfortunately, if I want to do this as a Calc 1 problem, I'm going to have some really nasty trig functions that arise. So as an aside, so I'll make this extra credit. Oops. Solve using Calc 1. All right, so we have about 2.5 minutes left. Has anybody ever read Click, Clack, Moo, Cows That Type? All right, so Farmer Brown has a problem. All day long, his cows like to type click, clack, moo, click, clack, moo, click, clack. I can't do this as well as I can do Cat in the Hat. I can do at least the first quarter, I believe, still from memory. It's been that long of a childhood for my kids. So imagine we have Farmer Brown, and we will meet their cousin later, and they will only consider square or rectangular pens for their cows. And given that you are at a school whose mascot is a cow, this is not an unreasonable problem for you to be concerned about. So imagine you have 100 meters of fence. You want to maximize the rectangular area. So one thing you could do is you could say the perimeter is 2x plus 2y equals 100. The area is x times y. And we could try to solve this using Calc 1 techniques. And one way to solve this is we can say, well, x plus y equals 50. So y is equal to 50 minus x. So I can consider the function area of x is x times 50 minus x. So the boundary is x equals 0 and 50. These are clearly going to be the minimum. And then I look for the critical points. How do I find the critical points of the function x times 50 minus x? Okay, how would I take the derivative of x times 50 minus x? I'm sorry? Yes. So you Thoreau it. Henry David Thoreau, phenomenal New England writer. You've made it when your name becomes a verb. What is his great advice to people? From Walden. No. One word, but he says it twice. Simplify, simplify. You could, of course, simplify to simplify, but you lose the emphasis. Before you ever do any algebra, always think about simplifying. If I write this as 50x minus x squared, it's going to be much easier to take the derivative. So then we get 50 minus 2x equals 0. We get x equals 25, we get a square. So I'm going to stop here. We'll talk more about this problem. We'll talk more about Lagrange multipliers in the next class. But the real key thing is, before you start doing a lot of painful algebra, stop and think, is there a better way to do it? It's worth spending a minute or two thinking, is there a better path than just going through and using the product rule? Product rule is not horrible here, but there's better options.